This video will discuss the principles and applications of the conservation of momentum. But first, what is momentum? Momentum is a vector quantity which describes the motion of an object. Often denoted with the letter P, momentum is simply the product of the mass of an object and the velocity of that same object. A striking feature of momentum is that it is conservative when considering closed systems of objects. We interpret this to mean that while the momenta of a group of objects in a system may change, the total momentum in that system does not change. Momentum is conserved. It is neither created nor destroyed. We decided to explore this concept using billiard balls. Our experiments utilized a camera suspended above a pool table. A tape measure is laid in the background for scale reference. We carefully recorded collisions between the different colored balls and analyzed the resulting footage. The white cue ball was dropped down a tubular ramp to acquire an initial velocity.
Alright, we used tracker software to determine the velocity and how the momentum was transferred from one ball to the other. In this video, the cue ball strikes the 8 ball and most of the momentum is transferred while the cue ball still carries a little bit. From the tracker data of the cue ball, we can see that the velocity has a constant deceleration until the point where it hits, and then it drops significantly and continues to decline. From the analysis of the 8 ball, it rests still until collision occurs, and then you can see the slope of the deceleration after the collision has occurred. In this one, we tracked the split momentum. The cue ball slightly hits the yellow ball first, which transfers most of the momentum to it, even though the red ball still receives some. Here is the slope of the cue ball before collision has occurred, and the slope after collision occurred. The red ball was at rest until collision, and then this is the slope afterwards, after collision.
Colored balls are initially about 1 millimeter apart. As the cue ball strikes the red ball remains almost motionless. Although the red ball doesn't move, the momentum provided by the speed and mass of the cue ball continues to travel until momentum reaches the blue ball. The graph displays speed and time of the cue ball as it undergoes the experiment. As it can be observed, the velocity of the cue ball is almost constant before the impact and completely stops after the collision with the blue ball. This graph shows that the blue ball remains stationary until momentum is transferred through the red and yellow ball to instantly acquire a constant velocity.
Similar to the pool balls, in this video we can see that when two tennis balls collide in the International Space Station, where no gravitational forces are in effect, the momentum is conserved 100% with no interference. When the tennis balls stick together, their mass is doubled, so their speed is halved to abide by the law of conservation of momentum.
We'll have half the velocity of the one initially that was moving. Conservation of momentum makes it actually quite interesting and challenging to move around the ISS if you don't have something to reach onto a handhold. Because if you get trapped out in the middle, there's no wiggling you can do, no swimming you can do that will get you over to a handhold so that you can pull yourself to move through the station.
This applies to more than just balls, though. In the second video, we are looking at two cars that collide with each other at the same speeds, yet have different masses. As we can see, the red car is pushing the blue car back slightly, because it has a greater mass, hence having more momentum. However, since the momentum is conserved, the two cars have opposite momentum vectors and very nearly cancel each other out, hence the reason that they don't move very much.
Much higher accelerations, hence much higher forces than the occupant of the heavier car. This is one reason why lighter, smaller cars offer less protection to the occupants than larger, heavier cars.
We hope you enjoyed learning about momentum and some of the ways that it can be applied practically.